Let's discuss about this work done by a variable force. First, let's discuss with this whatever formula of this work done. So we do have work done is equal to force times displacement times cosine of theta. Theta is angle between F and D. So it means this formula is easy to apply if your force is constant. But if force is variable, then you have different values of F. You have to calculate this force in every point, and you have to calculate total work done by adding them together, which is a bit difficult. So it means we can do such type of problem in graphical method. So let's first discuss with this simple one, which is constant force, and generalize it, use it into the variable force. So if constant force is applied on a body, if you plot a graph between force in y-axis and position in x-axis, so from moving from x1 position to x2 position, so x2 minus x1 is actually position difference, which is displacement. So x-axis from x1 and x2 is displacement, and force is over there. So if you think about this work, F times D, which is F is one side of this rectangle, and F to D is actually other side of this rectangle. So F times D is area of this rectangle. So which is actually work done? Yes. So it means the work done, we can generalize it from here. The work done is area under the force curve with x-axis. So we can generalize it to find the work done by this variable force. Let's consider a force which varies from point to point, and to calculate its work done. So there are several successive constant values. So in first case is force is this, and its position moves from equilibrium to some point 1. So you can calculate work done by this force by just taking area under this curve of this force curve, so which is work done by this first action. Similarly, it goes from 1 to 2, then force changes from this value to another value, then you will calculate the area under this curve. So from position 1 to 2, so you will calculate this area, you will get work done under this curve. Same thing from 2 to 3 and 3 to 4. And if you add them all together, the work done, this first part, second part, third part, and fourth part, you will get work done by this force in total succession, so which is total work done. Now let's say if you have like not constant in any successive point, so it's continuously varying. So let's say like this. So in this case, the force varies from x1 point is minimum and x2 point is maximum, so it varies continuously as a curve. So it's not like you can make a rectangle. So you have to choose a certain point and make some rectangle in some section, and other section. You have to make multiple rectangle, find the force times displacement in this section to calculate work done in this section. Same thing in second section, third section, fourth section, and add them together to calculate the total area under this force curve, and that is work done. Now this is curve, so you do see over there some part is missing and some part is adding, so this is just approximation. How do you make this approximation more better? So you're gonna make this rectangle as small as possible, like this. In second part, look at here, this rectangle is smaller than the first one, so your approximation is more better. Now if you make this rectangle as small as possible, then you'll get highest approximate value. And this is also we can do by this integration, which is highest precision value from this division of rectangle into small section and calculate into work done by multiplying force and displacement, or by calculating area under this force curve. Now let's take one example, which is real example, work done by this spring. So if you have a spring attached on a wall, and if you stretch it by applying force F, then it is moving that way. So force and displacement are same direction. So the force and displacement relation, if x is displacement, the relation is F is equal to kx. Force is proportional to the displacement. So this is force equation for this spring. Now the force is variable, so how far you will stretch, you have to apply more force. If you are stretching less, you have to apply less force. If there is no displacement, that means it is in equilibrium position, no force is applied. So if you plot a graph between force and displacement, from this relation you can see that this is a linear relation, straight line passing through the origin. Okay. Now if you want to calculate work done by this spring by applying this force F, now do you have to calculate area under this force curve? Yes. So it means you have to multiply this displacement, which is x-axis, and you have to multiply with this force y-axis and make it half, because this is triangle. If you look at triangle, then area of triangle is half times base times height. Base is on the bottom, height is this, so height is force, so that is half. Base is you do have displacement, which in this our case x is displacement over here, and height, which is force, that means kx. Now if you multiply them together, you will get half kx squared, which is area under the force curve, that is work done. So work done by the spring is given by half kx squared. So where x is displacement and k is constant, which is called spring constant. So work done depends upon how much you displace it. More displacement, more work done. Less displacement, less work done. But is it proportional to square of displacement? So look at here, force is proportional to displacement, but work done is proportional to square of displacement.